I think we need to start. So first of all, let's welcome Andrew. Andrew is from the School of Technology, University of Campinas, Brazil, and he will give us a very interesting topic about unsupervised strategy to the network topology reconfigurations optimization with limited link addition. So let's welcome him, and it's your time, Andrew.
Okay, thank you. Thank you, Chen. Thank you, Professor Menezes, for the opportunity to show our work about how to improve the efficiency of a network in an automatic way with the addition of a very small set of new edges. Our work unsupervised strategies to network topology reconfiguration, optimization with limited link addition (NTRLA) was conducted by my former master student, Mr. William Roberto Paiva, and it was supervised by me and my colleague, Professor Paulo Sérgio Martins. And I like to show you the context of your research. The review. Networks may grow unplanned, and usually they do it. And they grow according to the environmental conditions they can find in different domains. In this process of growing, most of the time the networks change their properties and they may deviate from optimal values. Properties like node degree, diameter, average shortest path, resilience, and efficiency. If you have an objective, maybe the parameters, the values are not so good for this objective. The general solution for this problem is network reconfiguration with the addition of new links, new edges, but keeping in place the previous ones, the nodes and the edges that already existed. Stating our problem, our research problem. We can summarize our question in how to choose the end nodes of a single new edge in order to improve the network efficiency. We have a special interest in spatial networks, but the problem is general. An example of this problem, the application of this question is how to choose an extra power line in a high voltage electric system to improve its efficiency. Let me show an overview of the work. We developed a series of strategies or heuristics to the problem. We performed simulations with scale-free networks and handle networks. I can say that this is the abstract part of your research. And we assessed the efficiency gains of each strategy in these models. And I can say we have a practical part, a real-world example. We analyzed a single power grid map, the power grid of our country, and assessed the efficiency gains of each strategy again. And we performed the evaluation of an exhaustive search to include new edges. This exhaustive search was based on the large instantaneous increase of efficiency for each addition. We simulate some scenarios. Both networks, the networks of the models and the map are sparse and connected. We prepared 1,000 realizations of each model, and to be comparable with the power grid, we used the same order and same size for all the networks. And for our experiments, we added 50 new edges in each network. For the models and map or for our experiments, we ranked of all the strategies according to the efficiency gains. For the exhaustive search, we attempt to find the maximum possible increase. We have some concerns during this work, and we already knew that exhaustive search is a NP-hard problem, not a general procedure, but we know that it may be applied to established network. Then if you have the network in place, it is easy or it is feasible to do an exhaustive search and to find the place to put the new edge. But this is not applicable to general problem and is very difficult for the planning of a brand new network. Our premises are we were looking for general unsupervised strategies that could be applied to a large number of realizations, to abstract models, and so. And we avoid topologies that are similar to complete mesh, star, or onion topologies, because they are very difficult to be built in the real world. Our method was the development of some strategies, a set of strategies, based in betweenness centrality, closeness centrality, and node degree, and the combinations of these three elements. We use an additional procedure, namely spectral bisection or mincut, that separates the network into partitions of similar sizes, and each point of the edge is chosen from one of the partitions. Our results. We performed experiments with the model, the abstract models, and the power grid map. We added the first 50 links in each experiment, and in this chart, we see the final state. The smallest gains were in the abstract models, scale free and random. We observed an amazing gain in the power grid map, about 40%. The spectral bisection increases all gains, then it appears to be a standard procedure from now on. And our best results were for strategies based in closeness betweenness. Only for the map, only for the real world power grid, we do the same, and we recorded the efficiency gain along the addition of new edges. The exhaustive search had better performance, but it's not guaranteed to have reached the global optimum. It is because when we did this experiment, we put an edge, the edge that brought the greater increasing in the efficiency. Then we repeated it and repeated it again. We have a good result, but if we put all the 50 edges at the same time, the global optimum could be different. Again, the spectral bisection improved our results, and for one model, for one strategy, we obtain 10 percentage points with the application of mincut. And the application of our strategies in the power grid map outperformed the network models. The real map had a better result than the abstract models. Our conclusions. We ranked all the experiments and all with the spectral bisection because the results are better. And the third main strategies. First, link the node with the highest closeness to the node of the lowest closeness. It outperformed all others, but tends to a star-like topology. Then we can apply a limited number of times. It's not a strategy that we could repeat and repeat. It is based in the closeness between us. The second strategy, link the nodes whose betweenness is nearest to the median of the network. Tend to a more sparse and feasible topology. It's easy to calculate. It takes a low computing time, and it is based in centrality betweenness.
Hi, Andrew. 5 minutes left.
Okay, thank you. The third strategy, link the non-terminal nodes of the lowest betweenness, and this strategy keep the terminal nodes unchanged. There is no scale limitations, and again, it is based in the centrality betweenness. I'd like to highlight some additional finds. The strategy that chooses the two nodes of the highest betweenness and links the neighbor nodes of the lowest degree had the worst performance. But if we analyze it in the point of view of efficiency gain, this strategy that has no good results with this objective uh, allows the creation of redundant paths, and it could be very good for the resilience of the network. Our objective was efficiency, then this is not a good strategy, but for resilience, it could be a good choice. And it remains open the question of what are the properties of that map, the real map, that allow best performance for all used strategies for this problem. We intend to investigate it in the future. Thank you for your attention.
Oh, thank you. Thank you for your interesting presentation, Andrew. And now it's a question session. So it is a very interesting talk. So I have a question first. So I can observe you compare different strategy to the different models like HLC. Like HLC did best for the PG. Yes, as
Yes.
HLC did best for the PG. And here we can only say that you observe this kind of phenomenon. Do you also apply some reason why this method can did best for HLC did best for the PG, or what kind of property? It's something like your open questions. What is the property of these things make this strategy did best for this model?
Okay, Chen, thank you for your question. We don't know what is the set of properties of these networks that changed the gain in this way. Scale-free models, the scale-free model is very common. It's a reference model, and we didn't get good results. For random networks, we have a slightly better result, but not so good. And as we can see in the chart, the real map, that is a concrete example, had an amazing result. And unfortunately, we didn't know yet what are the properties of the networks that could cause this phenomenon.
Mhm. Okay, great. Thank you for your answering. Here, Hugo have questions. Hugo.
Yes, thank you, Zexun. Andre, my question is regarding the feasibility or the cost of the HLC strategy, because um, the power grid network, if I'm understanding correctly, it is a spatial network. So the nodes, they have a location in the space. So perhaps a strategy in which we connect a high closeness node to a low closeness node um, could lead to us having to connect a very central node in the network to a node that is in the periphery of the grid. So how do you address the feasibility of adding these edges or the potential costs in terms of the distances that the nodes are from one another for you to add these new edges?
Okay, Hugo, thank you for your question. It's really a problem, and exactly because we outlined that team, the strategy is not good for the recurrent application because it tends to a star, and of course the central nodes in the physical network could be linked with the peripheral terminal or peripheral nodes, and it's not feasible in the real world, especially for this sort of problem, because the construction of a new power line is a very complex task, and we need more considerations, not only the topology of the network. We know about it. This strategy is not good for um, the application of repeated times but in the point of view of the first student or automatic um, selection of edges, this strategy could be applied if you want, for instance, to put it 3, 4, 10 new edges. There is no problem. But for a lot of new edges, we recommend that you think about the second strategy. Uh, it is not so efficient, but we don't have problems with centrality or centralization of the links. Uh, did I answer your question?
Yeah, I'm yes. Just to follow up that, my 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 understanding is that it can be a problem. This high to low closeness node can be a problem even to add one single edge, because this single edge could be like an edge of that's like 20 kilometers. I don't know, something that makes it unfeasible adding these one single line. Would that be the case? And if that's the case, what do you think would be the most efficient strategy that would find a best trade-off between the cost of adding a new edge and the gain in the efficiency of the network?
The best strategy is exhaustive search in this case, because if we think about an established network, we know the points, we know the nodes and the edges. It's possible to perform an exhaustive search to look for the best position of the new edge. Then, if you have a real-world network, a spatial network with the nodes in place, the edges in place, try to do the brute force analysis, and you will find the best position. But our intention is to investigate more abstract or situations where we cannot do it because we don't have the network in place. For instance, for abstract models where the physical position is not important at the beginning, we did the same analysis, and we take the models as spatial network, which didn't change the position, but it's true that for us, we are not considering the length of the new edges, because for Brazilian electric system, it could be 1,000 of kilometers. Then, according to the model, the topology of the network, our strategies could be used to project a brand new network, to examine, to test a huge set of abstract networks. But as I state, if you have the network in place, as for instance, established power grid, you do better if you perform an exhaustive search of first brute approach to the problem.
Thank you, Andre.
Thank you for your presentation, and thank you for your answering. So now can you stop sharing, Andrew?
Okay.
And since we don't have the first one, so next one will be track hand. So track hand, can you share the screen? Now you are co-host, so you can share the screen.
Just one moment, I'm trying to figure out how this works.
Okay.
Let's see if this works. Share.
So the next talk will track Han.
Yep.
He is from Institute for the Theoretical Physics, University of Cologne, Germany. And his talk is about the reconstruction of demand shock in input and output network. So Chuck, can you
am I not sharing the right one? Okay, just one moment. Let me stop sharing. Let's try again. Huh. Maybe it's this. Is this correct one? Because yes, I can see my presentation. I can't see. Okay.
And if you don't mind, you can turn off. You can turn on your camera. Yeah. Thank you.
I'll switch on my camera. Can you see me now? Because I can't see anything by myself. Okay, great. Thanks for the introduction, Zexun. So hi everyone, my name is Chuck Han, or Chengyuan Han is my Chinese name. I'm coming from the Research Center Jülich in Germany. I'm also affiliated with the University of Cologne. So today I'm going to talk to you about the reconstruction of demand shock in input-output networks. So when a disaster happens, the demand side, the consumer demand side, is normally first affected by such disaster, and there will be an economic shock that propagates eventually to the production side of this network. The policymakers and the economists would like to understand and reconstruct such shock in the demand side so they can build a better economic network afterwards. However, this reconstruction sometimes is not possible due to limited data on the production side. So in this talk, in this project, I will talk to you about the work we did. We're using some assumptions and some properties of such demand shock, and some algorithm from sparse signal recovery, trying to reconstruct such demand shock. So let's get started. First, let me quickly introduce the input-output analysis, also known as input-output network ion analysis. It's a quantitative way that represents the interdependence of different sectors or different countries, how the economic goods are being transferred or economic capital being transferred among them. The table here you can see is an example table. Each of the elements here represent from one industries in one country to another industries in another country. The columns on the right here is called or final use by the countries, which means the final products is going to the consumer markets, which will denote as final demand in this talk. This whole idea, this whole model was developed by Wesley Leontief, and he was awarded the Nobel Prize back in 1973. So put into in a more mathematical formula, we can write the balance equation of input-output analysis as the one showing on the top, where xi is output of sector I, aig is the proportional transaction between sector I and sector J. Is also known as technical coefficient. Actually, I should say from sector I to sector J, and the fi is the final demand to each of the from each of the sector. The s is the number of sectors. So this means the outputs of any given sectors have to go to either one of the other sector or to the final market. We can rewrite this into a linear algebraic form, where x is equal to L times f, where L is known as Leontief inverse, is just identity matrix minus the technical coefficient matrix and the inverse of that. So now we introduce a shock to the demand side, delta F. And because of with the previous equation, we can see there will be a change on the production side as well, and we will name it delta X. We have one assumption here, is this shock on the demand side will be sparse, which means only a few sectors on the consumer side would actually be affected. That means there's only a few non-zero elements of the delta F. The problem of reconstruct such delta F is that we don't have a full knowledge about delta X itself. So we only have a few observations coming out of delta X. This means the system is actually underdetermined. So the question arises: can we still reconstruct the initial shock delta F with such limited information? I mean, of course, the answer is yes. Otherwise, it wouldn't be here. So let's just go into the question a little bit more. This question basically coming down to we have to use the structural information of the delta F to find out to reconstruct the signal. What we can do is we minimize the number of non-zero elements in delta F, also known as the zeros norm of delta F. So we can find a solution that satisfies this equation on top here. We will consider three different methods that to reconstruct shocks coming from sparse signal recovery. The first one is called convex relaxation or L1 minimization. So the idea is we convert the zeros norm into the L1 norm. So instead of just minimize the number of non-zero elements, we minimize the sum of all the elements in delta F. The second method is orthogonal matching pursuit method. It's a matching pursuit method. Idea behind it is we know the delta F is sparse, so we just only a few columns, only a few columns of L would participate in the multiplication process. So we just testing different combination and superposition of them to see which one contribute the most, and we find the delta F itself. And the last one is compressive sampling matching pursuit, which we will refrain as a cosam from now. This is an enhanced version of the previous one, OMP. Instead of just checking one column at a time, it's checking multiple columns and remove multiple columns to see which one to better find the results and in a faster pace. So I'm going to show you the results immediately now. You can see there's two parts of the plots. On the top here is each of the plot represents one of the methods I mentioned right before. The blue region bar in the bottom is the one that where the reconstruction is not successful. So basically we compare the delta F, the reconstructed delta F, and the real delta F. See whether, and on the yellow side means the reconstruction it is successful. The plots here is just sum up vertically of each of the plot and put them together. From both plots, we can see the reconstruction is possible. It works better with the cosamps. It is a better method from here among the three that one we tested. And also we know that it's have a higher chance to reconstruct the delta F when we have a less element in delta less non-zero element in delta F, and more observations come from delta X. So, and also from now on, we're gonna only using the cosamps and to study that, since this is the best method among the three we tested here. Okay, so we know the cosamps can reconstruct the delta F. However, in the real world situation, we don't have the privilege to have such a perfect delta X, even though it's only a few observations come out of the entire all the sectors. Sometimes those observations are noisy, so we want to test whether this algorithm is robust and can it still reproduce the reconstruct the delta F when there's noise presented in the observations. So what we do is we're adding n noise points in the observed delta X, and they are ranged from 0 to sigma, where sigma is known as the noise strength. Then we compute the difference between the reconstructed delta F and original delta F, and we find the norm of that. This one known as the difference. If the difference is smaller than the 10 to the power of -5, we define this reconstruction being successful. If not, it's not. Otherwise, it's not. We also choose 3 lines along the 100% success rate boundary on the previous slide plots, where we basically see at 3 different situations, where it's low sparsity, low number of inputs, medium sparsity, medium number of input, and high sparsity, a high number of input. 3 different cases to see whether this will affect the reconstruction itself.
Hi, Chong. 5 minutes left.
Yeah. Okay. Thanks. So here's some result. First we test the robustness of the algorithm itself. The dotted line on the bottom reference as a linear region between the difference and the sigma, the noise level. You can see here all 4 lines, each of them represent a different number of noises in there. They all increase mostly linearly with the noise level. And we can see that the difference is actually not strongly affected by the number of noise that in the added to the system. So we can see the reconstruction process itself is actually robust against noise. So here are some more results that when we test one, see whether with the noises the reconstruction can be successful. You can see from both of the graph is come from the same set of results. We just present them in a different way. We can see from both of them here is that the reconstruction absolutely is possible, however, with certain limitations on there. When the uncertainty is big enough, it will reduce the possibility of reconstruction. And we know that if the number of noise is bigger than 3, number of noise points, or the sigma bigger than 3, or the sigma is bigger than 10 to the power of -4, the reconstruction become extremely unlikely to happen. So quick summary on what we have done so far. So we have shown you that it's possible to reconstruct the demand shock in an input-output network. We showed the cosamps is a better method among the other 2 we tested. The algorithm itself is robust against small noise, but when the noise is large enough, such reconstruction become unlikely. And this is another thing that I already didn't show in the presentation here, is that if we can't, even if we can't define the shock, quantitatively, we can still find where this originated from. So we can define them quantitatively, and we hope using both the origin and the impact of the shock to help to help the policymakers enhance the resiliences of the economic network. And here is a list of references used in this project. Come to here. Thank you very much for your time, and I'll take any question. Thank you.
Thank you. Great, thanks for your talk. And it's very interesting. I have a question. Can you go back to page 9?
Yes, yeah.
So here in the page 9, we can find, generally speaking, here the co-CNMP did the best, but I found with the increasing number of the input n, all the 3 methods go to the same. Is that to say, after a lot of number of inputs, this method can do the similar?
So you mean here, right? You mean this part here?
I mean the second picture. You can see the number of.
Oh, you mean this point here?
Yeah,
okay.
Yeah.
So the data itself is coming from the, as I indicate here, the data itself is coming from a database called Word Input Output Dataset. So it contains 56 sectors and I can't remember, I think 40 or something countries and regions. So we boil this whole big table down to just 56 times 56, so just each sectors. So at this extreme, at this last dots here, where they all converge to 100% success rate, it's actually the system itself is fully determined.
Okay.
So that's why they always 100% success rate here. So yeah.
Got it. Thank you.
No problem.
And here, Ronaldo also has a quick questions about collaboration. Can
you? Hi, Chuck. Thank you. So it's just I may have missed in here because you said. So how do you define a sparse shock? So I'm just I'm not sure I caught that.
How do I define in the calculation itself, or how do I define it? I mean, or why is it sparse?
No, yeah. What is considered a sparse shock as opposed to dense one?
Well, sparse. Okay, so the sparsity itself actually this is wrong here because the sparsity actually should be the number of zero elements, zero entries in the vector. But what we define sparse is, so in our case, we goes all the way up to 15. We test different scenarios and just randomly generate the values for each of the sectors on the demand side. I guess as up to 15 it would be so there are not more than 15 sectors being affected by this disasters, let's say. So that will be sparse. If more than 15, we don't think this is sparse signal anymore. It will be more difficult to compute. Of course, I mean 15 is just arbitrary number we find. So
yeah, so that was my clarification. So I mean, you saying all the way to 15, you don't consider sparse, but I was wondering if there is an agreed upon.
No.
Okay.
This is just what we come up with. It's just an arbitrary number. I mean, of course, you can look here as a cosine. If you just follow the curve, it's probably gonna go up something extremely higher with for undetermined system still can reconstruct such thing, right? We don't know. I didn't test it, but we think that if it's more than 15 sectors being affected, we wouldn't consider it sparse anymore. For instance, I can give you a quick example. At very early stage of this pandemic, we say, oh, this is great. Maybe we can actually use this on some real world scenarios. And as soon as the whole world got affected and being locked down for more than 3 months, we realized this is no longer makes sense because too many sectors being affected on the demand, or on both demand and production sides. But yeah, eventually just too many different sectors being affected. The base of this project is no longer making sense to test.
Thank you.
Thank you.
Any other questions? Thank you for your answering. Is there any questions?
Chen, I think the first speaker is now online.
Oh, okay. Yeah. Can you set him as a co? So, Chuck, can you stop sharing?
Yeah.
Thank you. Okay, so I think now our first speaker is come here. And so Pivithuru, can you share your screen?
Yes.
So our next talk will be given by the Pivithuru from Department of Electrical Engineering and Computer Science, Syracuse University. So the topic is about very interesting talk about node classification, node classification with bounded error rates. So Pivithuru.
Yeah, I'm having some trouble sharing this.
Okay.
Screen. Yeah, let me.
This is Ronaldo Menezes. So do you see the button on your screen to share, or because
yeah, there's like some like system preferences I have to change.
Oh, okay.
Yeah, let me.
No, I was just making sure that was not on our system here. Okay.
Yeah.
So, Pivithuru, would you prefer if we go with the next speaker, and we can come back to you at the end of the session? Would you prefer we do that while you solve that?
Hi, Pivithuru.
Yeah, let me try again. So I have been disabled from screen sharing.
Zexun, maybe you can make her a co-host again.
I'm making it. It's done. I don't know why it stopped. So it's okay.
Oh, now we can see your screen. So
okay, cool.
Full screen.
Yeah. Okay.
Okay, now it's your turn, Pivithuru.
Yeah.
And go back to.
So sorry for the technical difficulties. So I'm Pivithuru. I'm from Syracuse University. This work was done in collaboration with my advisor, Dr. Sucheta Soundarajan, and my collaborator from Naval Postgraduate School, Dr. Raluca Girard. So this work is about node classification with bounded error rates. So generally, a classification algorithm, you have some label data and you want to predict labels for the new data that you don't know a label about. It's the same for node classification problem as well. In this case, we have a partially labeled graph, and we want to predict labels for the unlabeled nodes in this graph. The difference between traditional classification algorithms and node classification algorithm is that node classification algorithms are designed to consider the relational nature of classification entities. So they consider not just node attributes, but also the connectivity patterns between these nodes. So some applications of node classification algorithms are like, if you know gender for some population of this graph, you can predict the gender for the others. You can predict relationship status as well as political views in social networks. So the motivation for this work comes from often we use these classification algorithms to make sensitive decisions, some predictions that can have adverse effect on entities. For example, say you have a graph partially labeled as people as criminals or not a criminal. And you want to predict for the rest of the graph whether they are criminals or not. So in this case, predicting someone as a criminal can have very adverse effect on people. So we want to be confident about this prediction we make, not just about what is our prediction. So in such applications, it is important to associate a confidence in each prediction. You can say we predict this person as a criminal and we are 90% confident about our prediction being correct. That's where the conformal prediction framework comes in. So this framework has been used in other typical classification problems, basically for like how do you do conformal prediction for decision trees, random forest, and so on. So in this work, what we do is we show how we can use the same framework to provide bounded error rates for node classification algorithms specifically. So one question that you may ask is, say why can't we use class probability as the expected error? For example, when you make a prediction, if you use something like logistic regression or some other algorithm, we usually have a class probability, like probability of this instance belonging to this class. So one question may be, why can't we use that probability as the expected error or the confidence we have in prediction? So we ran a simple experiment considering this class probability as the expected error, and we compared that to the actual error we see in these samples. And also we looked at the expected error from conformal prediction, and we compare the error rates in both these scenarios. So as you can see in this graph, so that when you look at the class probability, expected error rate is not always the actual error rate we expect, but for conformal prediction, the expected error rate is always below the actual error rate that we say it would be. So that's why we think conformal prediction can give us better confidence to associate with our predictions. So this framework was introduced by Schoeffer and others. And so this framework provides bounded error rates for considering how typical a data instance is. So suppose we have a training data set, say up to like we have n data points. What we do is we divide this data into training data as usual, as well as calibration data. So we will use the training data to train our model and test our model and all that. Then what we do is we use the calibration data to conduct the conformal prediction. So what we do is say that, say in this data set, there are L classes an instance can belong to, say if it's like 2-class prediction or 3-class prediction and so on. So what we do is, with respect to the calibration data set, we look at, say we have a new example that we need to assign a label to. What we do is, with this new example, we'll consider all possible labels it can take, and we look at how typical this sequence, sequence with respect to calibration data set looks like with respect to each label. For example, if there is a very highly unlikely label that we are considering, the p-value for that would be very low compared to some label that can be the actual label. So what we do is we predict all labels that satisfy the given significance level as the labels for this new instance. So what this means is so one example can have multiple predictions in this way, because like say if you predict all possible labels as possible label for some instance, you have 100% confidence in the prediction, right? Because you predict everything as, but once you like start removing these labels, your confidence level drops. So because of this, in order to satisfy some significance level, some instances may have to have more than one prediction in them, but the optimal algorithm will have one prediction for each instance. So in order to apply conformal prediction for node classification problem, and in generally, in order to apply this conformal prediction framework, this data, the training data and the calibration data need to satisfy the exchangeability assumption. Because in order to generate the prediction in order to generate the significance level. Conformal prediction framework uses a test for randomness. So in order to use that test for randomness, this permutation that I talked about earlier need to be every permutation of this sequence need to be equally likely, meaning that this data should be exchangeable. So when we want to apply this, we need to show that the data we are using is exchangeable indeed. So for node classification data, even though this data is connected and they have connections with each other, what matters is how we sample this data to train, how we sample this labeled data in order to train our model. For example, if we use an algorithm like BFS or random walk, this data is not exchangeable because there's an order that you follow in order to collect your training data. But if you randomly sample this training data, in that case, this data become exchangeable. So this is part of our future work as well, to look at how we can modify this framework, because we cannot really depend on how we sample the data in order to apply the algorithm. So that's like we are ongoing work about like how we can generalize this to other kind of sampling algorithms. The second thing that we need to define to apply this conformal prediction framework is defining a conformity measure. So the conformity measure measures how typical this new sample is. For example, how one such measure is probability margin. So you look at the difference between the label probability for the label that we are considering with respect to the highest probability for any other label. For example, say there's an instance with probability, the predicted probability with 0.9 for one class and 0.1 for the other class, then the probability margin would be very high, like 0.8. But if there's an instance with 0.6 probability for one class and 0.4 probability for the other class, then the probability margin would be pretty low. So in that case, we would be less confident about this prediction.
I think so 5 minutes left.
Yeah, so this is the conformal prediction. This is the conformity measure we use in our application. So we run experiments using different types of node classification algorithms. We wanted to show that it works generally for all types of node classification algorithms. So we use iterative classification, label propagation, graph convolutional networks, as well as deep walk, like node embedding based classification. And also the evaluation need to show that the prediction we make meet the specified error bound. If we say the error should be less than 5%, the prediction we make should meet that error boundary. And also how accurate these predictions are. And lastly, how efficient these predictions are. I mentioned earlier that the conformal prediction can have more than one label, but in order to make an efficient prediction, it needs to be how many one-class predictions we make compared to how many multi-class or how many zero-class predictions we make. So I have results here for one algorithm that we tested, the iterative classification algorithm. As you can see, this purple line here, error is always less than the significance level that we specify it would be. So if we say significance level 0.25, that means the error should be less than 0.25. And when we use this for our predictions, the error is always less than that. And also we look at the accuracy. If it's always better than the baseline accuracy that we would say from the classifier. And then lastly, if you look at the efficiency, like how many one-class predictions we make and how many multi-class predictions we make, at about, say, 0.15 significance, our efficient is almost 90%. So that means for 90% of the training data, we predict one-class prediction. So I think that's a very good statistic. So in conclusion, we showed how to obtain bounded error rates for node classification algorithms, and also we showed how exchange assumption can be met from this, as well as what conformity measure to use. And also the experiment analysis showed that the conformal prediction have maintained the specified error bounds while providing efficient predictions. Thank you very much. Any question?
Great. Thank you. Thank you for your interesting talk, Pivithuru. And I also did some research on the classification. So I like your work, and I have simple questions. Mm-hmm. So what's your, as far as I I understand CP, the method of CP or ICP, should stand on a base classifier. So what is a base classifier? Logistic regression or SVM?
We use logistic regression here.
Okay.
Yes.
So did you have you tried any others like SVM or random forest?
For this work, no, we did not. Since we wanted to like diversify the types of classification algorithm, like node classification algorithms we use, we didn't dive into different types of like predictors we can use for ICA specifically.
And this kind of method like IP or this is C what's the so your method can be applied to any other classifiers, base classifiers.
Yeah. So the only thing that needs to be satisfied is the exchangeability assumption. Once that's satisfied, you can apply to any predictor. Yeah.
So okay, great, thank you. Any other questions? Oh, maybe I have another one, because you said here for the data set, you choose the you have the training data set to train the model, and then you have the calibration data set. So how to choose this kind of calibration data set?
Oh, so I split like training data, like I use 10% of the training data as the calibration data. So for example, in each of these example, like say there's like 30% of the graph labeled. So 10% of that would be used as a calibration data.
Okay, so you choose them randomly.
Oh, yeah.
Okay.
Completely at random, yes.
Makes sense. Great. Any other questions? Classifications. Okay, so no questions. Thank you. Thank you for your presentation, Pivithuru. So can you stop sharing? Okay, great. So last talk is from Guillermo. So you said
yes.
Okay.
Can you hear me? Yes.
Yeah, great. Can you
Great.
share your screen?
Yes, let's see. Let me see if I can get the right one.
So the green button in the bottom.
Yes, I have the green one, but I have
you need to choose the windows. You need to choose the windows.
But now I can't see this other one. 1 second. Let's see. And do you see my screen now?
Yeah, now I can see the screen, but not the full screen.
Yes.
So you can full screen.
That should be, yes.
Actually, it's not full screen.
Well, otherwise I can't. I think I saw it somewhere here.
Yeah, I think your Firefox browser presents the. You can have a try.
Well, otherwise maybe I can just do it like this. If I give me a few more seconds.
I think on the address bar there is a
this one here, yes.
Yeah, this one.
Great. Okay. Yes. Great. Thank you. That's it.
Now you can change to present mode.
Present here, right? Okay. Is it working now?
No, you're probably sharing the wrong screen, so you have to do that and share the correct one.
Okay, let's try once again. Okay, I think now should be.
Okay, that's fine. Great.
Yes. Okay, good.
Okay, so the next talk will from Guillermo, and he is from School of Electronic and Computer Science, University of Southampton, UK. And his talk is about Zealotry and inference maximization in the vote model, when to target potential Zealots. So it's a very interesting talk. So it's your time.
Great, perfect. Yes, thank you so much for the presentation. Yes, I'm Guillermo Romero. I'm in University of Southampton, working with Marcus Brede and the team there. On this topic, we focus on influence maximization in different contexts. And this work is about zealots, having zealots in the system. So to give a bit of context, this work is in the research area of opinion dynamics, where typically you have a network, which represents like a social network, a society or some community. And then the links between the nodes are individuals, the links are the social ties between them. And typically you have individuals with opinions, which are represented as a variable that can be discrete or continuous. And the individuals copy the opinions of the neighbors, or they are influenced by their neighbors, and they change their opinion in this manner. So there is some dynamics going on to the diffusion process, and the system evolves. And this research field focuses in many aspects of opinion dynamics. In particular, we are looking at influence maximization, which looks at how external forces or external controllers may try to tamper this opinion diffusion and get to different goals. For instance, to get one opinion more prevalent than others, or to affect polarization, consensus, or different aspects. So this is useful in in different applications, such as marketing, policy making, such as raising awareness, political campaigning, or even technological innovation, if it's taken out of the opinion dynamics stream. So here we focus on the role of zealots. So zealots are people that they are stubborn, so they don't change their opinion as easily, or they are biased towards one of the opinions. So even when the neighbors of this person, the social relations, have one opinion and they have the opposite, will have more difficulty to change. So zealots have been also studied for already quite a few years, and they are very relevant because it was found in simulations and models that even with very few zealots in a population, their opinion may take over the whole population, even if the population previously had the opposite opinion. So their role is very important. And in this sense, we are looking at influence maximization with zealots. So the question here is it worth trying to convince a zealot? So if you have the influence maximization context, would you go to target zealots and attempt to convince them even if they are harder to convince? Or would you go to ignore the zealots or to try to convince zealots through normal agents, and then that may try to convince the zealots? So we started this question in a different context, such as different levels of zealotry, which is this QI. So zealotry can go from 0 to 1 in our model. 0 is completely unbiased, and 1 would be someone that is full zealot, so it cannot change the opinion at all. And then we have also studied different topological places of zealots, a number of zealots. So I'm going to explain now the model that we use is the voter model, which is a very classical model in opinion dynamics. The voter model works that you select one node at random, then you select one of the neighbors at random, with a probability which is proportional to the link weight between the nodes. And then the first node copies the opinion of the second node. With the zealots here, we have this probability that opinion B is copied with probability 1, but opinion A is copied with probability 1 minus Q. So all nodes in the network, we are saying that, or the nodes that are zealots, are zealots towards opinion B. They are biased towards B. And the influence maximization in this context, we put an external controller, which is this squared node here, which favors opinion A, and then tries to have as much opinion in the network as possible. And to do so, it connects to nodes in the network with these links. We have a strength A subscript I, and it has to choose how to link to the network in the optimal way to maximize the opinion. So there's this decision of who to target in some sense, with how much strength as well. So this is a bit for the method we use. We look at the probabilities of nodes of adopting opinion A, because the model is stochastic. So we look at the probabilities and the expectation, how the expectation evolves. We build these rate equations to draw the evolution of the dynamics. And then we look at the steady state. So we look at the equilibrium, and the optimizer, the controller, tries to get as much as possible in the equilibrium. Well, because it's a different system, or a system of differential equations, and we have to use numerical integration to get to compute the steady state. And then we look at the influence maximization problem, which is how to specify this A, which are the links from the external controller, subject to the budget. So all link weights must be less or equal than a scalar, which is the BA here. And the weights must be positive. And we use gradient ascent for finding this optimum strategy. So first we start with a complete graph as a simpler example. Because of its high symmetry, we can actually get to, we can find analytical solutions and compute the maximum analytically. So the question here, we have a fraction row of nodes in the network that are zealots, and the rest are normal agents that are unbiased. So the question is, how much of the budget should be put onto zealots and how much to the other agents? And then the solution we get is this one here, which says that it depends on row, it depends on the level of Zealotry, QZ, and the budget. And interestingly, the budget is playing an important role there, because if you have a large budget, you should go to target Zealots directly. And if you have a low budget, you should go for the normal agent. And actually, we have here the experiments, both numerical and analytical. On the y-axis, you can see this is the alpha, which is how much is given to Zealots. And above the orange line means that Zealots receive more allocation than normal agents. Below, normal agents receive more than Zealots. So you can see basically, for instance, if the budget is very high, which is the dark blue, Zealots receive more allocation, more target than normal agents, almost for any level of Zealotry. So Zealots should most of the times be targeted. However, if the budget is low, which is the light green, you can see that Zealots are only targeted if their Zealotry level is very low. However, on the other hand, if the Zealotry level is slightly higher, only normal agents are targeted. So there's this interplay between the Zealotry level and the budget. Next, we analyze a bipartite graph to look at the roles of hubs and periphery nodes. So in this case, we have a fraction row of the graph of the nodes in the graph that are from one side of the bipartite, and another fraction 1 minus row is the other side. So there is this relation with the links, the hubs, the row that is the smaller, therefore is the hubs, which are much more links than the other. So the question here is how much of the budget should be given to hubs and how much to periphery nodes. And we set here the Zealotry levels antisymmetric. So the more the hubs are Zealots, we set the periphery to be less Zealots, and the other way around, to look for a different range of Zealotry levels. And here the results we find, they're also interesting. If we look first, again here, this graph is how much is given to hubs. So above the orange line is that hubs are given more than periphery, below periphery are given more than hubs. If we look at the dark blue line, which is a very high budget, we see that hubs are almost always preferred. Whatever Zealotry level they have, hubs are preferred over periphery. If we look at the light green, which is a rather low budget, we see that hubs are preferred if their Zealotry level is very low, is rather low. But then there is a very sharp transition to periphery nodes, even when the periphery nodes have a bit more Zealotry level than hubs. So this effect is reversed. And then finally, we look at the more complex networks, a Barbasi-Albert heterogeneous network. And here we set 20% of the nodes in the network randomly chosen to be Zealots with a Zealotry level QZ, and then the rest are normal agents. If we look first at the question again of how much is given to Zealots, actually we find that the answer is very, very similar to the complete graph. So these are the results for the Barbasi-Albert on the bottom left, and the bottom right from the complete graph, and we get very much the same. If you have a high budget, you go for Zealots. If you have low budgets, you go for normal agents, and there's the same interplay. So the topology doesn't seem to affect that much when it comes to this question of how much is given to Zealots and normal agents. However, if we dig a bit further and we look at the role that node degrees have, and in the interplay of Zealotry and node degree, we get a more interesting pattern. So in this case, we look at how much allocation is given to each node depending on the degree of the node. Here in these plots, on the left, we have the Zealots. On the right is the normal agents. Let's look first at the low Zealotry level, Q equal to 0.3 in yellow.
You have 5 minutes.
Yes, perfect, thank you. So when the Zealotry is low in yellow, we can see that there is a very sharp correlation between node degree and allocations. So hubs are given much more allocation influence than periphery. However, if we increase the Zealotry level to 0.5 in orange, we see that when it comes to Zealots, only peripheral Zealots are targeted, although normal agents keep the same correlation that hubs are preferred. If we keep increasing up to 0.9, which is very high, Zealots are not targeted at all. And normal agents, there's again a reverse in the sense that hubs are avoided and peripheral are preferred. So we can see this, we extend this analysis to the whole range of QZ. Here we show the correlation coefficients between node degree and allocations. And we see, for instance, well, let's look at the Zealots on the left, bottom left. We see that for low Zealotry, there is a very high correlation, almost equal to 1. So hubs are preferred. Then there is a transition where the correlation goes negative. So periphery nodes are preferred, and then goes to 0 because Zealotries are avoided. And the same happens in the normal agents on the bottom right. They start with positive correlation, then there's transition to negative correlation. So from targeting hubs to targeting peripheral nodes. And interestingly, this transition happens earlier on Zealots than on normal agents. So to conclude, we have found a few interesting behaviors when it comes to influence maximization with Zealots. We first have seen that budget is relevant. Well, the combination of budget and level of Zealotry. So if you have a high budget or the level of Zealotry is low, then you go to target Zealots directly instead of normal agents. However, if the budget is low or the Zealotry levels are high, you go for normal agents. Second, as we have seen that hubs, again, are related, targeting hubs or periphery nodes is related to the budget or the level of Zealotry. So high budget, go for hubs, low budget, go for periphery nodes. And lastly, we have seen this pattern that also then with node degree, there is this interplay of Zealotry and the node degree. So first, if the budget is high or the level of Zealotry is very low, you would go for hubs and also more for Zealots. Then you would go for hub normal agents, but peripheral Zealots. And then you will go for peripheral normal agents. This is all. Thank you.
Great. Thank you. Very interesting talk. Thank you, Guillermo. And I have a small questions. So now before that, I don't know anything about Zealots. And after this talk, I know a little about that. So here, my question is, how about if the same network exists two opposite external controller? Does it okay for?
Yes. We started having only one to simplify the whole analysis. In the beginning, we thought about having two external controllers. Other works we have done, we always include two external controllers. But this one, to keep it simple, I think the behavior is similar. Actually, I have done some experiments, and we included two external controllers and also Zealots for the two types. So Zealots in favors and Zealots against the external controller's opinion. And we actually found this a bit of the same behavior but extended. So if you have very low budgets, you would first target the Zealots that are in favor of your own opinion, then you go to normal agents, and then you go to the Zealots that have the opposite opinion as the budget increases. So there is, so it's similar behavior than for this simpler case.
Great, thank you. Thank you for your answering. Here, Ronaldo has a question. Hi, Ronaldo.
Thanks, Chen. So Guillermo, it's more again as of a clarification, right? So when you talk about the level of zealotry, is this for all the nodes in the network, or is this just for the ones that you say that are the zealots, right? So that meaning if the level of zealotry is very high, does it mean that everybody is stubborn?
No, it's only for the zealots. So we have typically a percentage of nodes that are zealots with zealotry level QZ, and then the others are normal agents. So in most of our experiments, the number of zealots is 20% of the whole network are zealots.
So now that you clarify that, so do you see the same sort of transitions if you vary the number of zealots in the network? Does it matter? For instance, if you rather than 20% being zealots, if you have half of them?
We don't have experiments with other with other fractional zealots. I would expect to see similar behavior, but probably shifted in the sense that you may need more budget or for do the transition or lower levels of zealotry. This is what I would expect, but as I said, we haven't carried out. Well, I think I may have some experience, but it was some time ago, so I don't know if. But we haven't looked into detail in any case.
Yeah, but thank you very much. Zishan, there's a question on YouTube. I don't know if you can see, but if you can't, I can actually read the question.
Yes, I can see. Here, Zoom, okay. Diogo has one. Hi, Diogo. Hi, Diogo, are you here? You said you have a question?
I have to enable him. Just a second.
Okay, yeah, you have.
Hello, can you hear me?
Yeah.
Yes.
Now I can.
Hi, Guillermo. I have two questions. One is related to what Ronald just asked. So if you have like a threshold or the zealotry level, and you can go for totally stubborn that you change your mind never to zero, or you can change very often, right? So a normal agent, it's somewhat some percentage of zealotry. So what's the level of zealotry of a normal agent?
It's equal to 0. So it would be Q equal to 0 in the model. So it would, a normal agent copies opinion A or opinion B with equal probabilities.
Okay.
Yes.
And the other question is like, can we consider like bots as zealots? In terms like you have bot, you program a bot somewhere, and the bot is programmed to do something, so it will never change their ideas. And if so, does your study is a message reinforcing that we really need to care about bots and really have to try to take them down? Because like if you have a large budget, in the sense that it's the most effective way to stop these disruptions of the normal flow of conversation, so targeting the bots, it's a good idea?
Okay, yes. Well, the first question, definitely yes. Bots could be considered as zealots in this context. Actually, Zealots, in this case, I have a single node, external node as Zealots, as a external controller that is a perfect Zealot. You could have as many as you want in this case. And to the second remark, definitely yes. I mean, I do agree. I do think that bots are definitely effective at affecting the opinion in general of societies. There's been, well, we have had quite a lot of news and we heard many things about international forces trying to influence democratic processes and these things. So definitely I would say that there is something there that we should be very aware and should be fighting, kind of, at least be very aware of it when people use social media and everything. There's quite a lot of intent to manipulate and affect opinions.
Thank you.
Thank you for your answering. Here are two questions via YouTube. And the first one is, have you checked if other characteristics of the network's topology, such as the density, clustering, coefficient, moderately affect your result?
No, we haven't checked. Apart from the three topologies that I've shown, we didn't explore much further. So I don't know other characteristics. In the case of the whether to target Zealots or not, we saw that there was very, very similar results from the complete graph and the Barabasi Albert. So we expect that there shouldn't be much difference there. I don't know if other specific networks with strong community structures and then Zealots placed in strategic places, maybe in these cases we would see something different. But as long as the network is general enough, I wouldn't expect much differences in general.
Oh, the last question, I think, due to this, Zealots are influencing their neighborhood's behavior. Have you considered community hubs to select your Zealots or other seeding strategy?
We haven't really considered exploring this, but I mean, as I just said, it could be interesting. Like, there could be different results and potential interesting behaviors if we consider communities and other topologies.
Okay, great. Thanks, Guillermo. Thank you. So now, can you stop sharing?
Yes.
And I think now we finish all the sessions of this this online events. And great thanks for everyone's help. Great thanks for your attention. Great thanks for the speakers. And I think here are some words from our chair of the organization community, Ronaldo.
So thank you, Zexun. So actually, I'm co-chair with my colleague Giuseppe Mangioni, who is actually online as well. So I'd just like to thank everybody for participating. We had to put this sort of last minute, but I think it worked fairly well given the short constraints that the short time constraints we had. So I hope that next year things are going to go back to normal, whatever normal is, and we can actually host the event. We were quite happy with the results that we had here in Exeter. Was probably the most successful event we had in terms of attracting number of submissions. So we're hoping that this is going to happen again next year. So you guys stay safe. I hope, again, I wish you all the best, and hopefully we'll see each other in person next year here in Exeter. Thanks a lot. Bye-bye. Thank you.